Hello, my name is Hyunbin. I will talk about this topic, counter. Asynchronous counter are also called ripple counters. The front flip-flop is used as the input to the flipped flip-flop. Asynchronous counters are simpler than synchronous counters, but have the disadvantage that they have a higher propagation delay. The asynchronous counter is the clock pulse input of the first flip-flop, and the other flip-flop is used as the clock pulse input of each flip-flop. Asynchronous counters are usually used as JK flip-flops. And synchronous counters have the advantage that pulses are applied simultaneously to all flip-flop inputs and the outputs are synchronously changed. Synchronous counters use the D flip-flop to design the funnel.
The counter is a logic circuit for counting the number of clock pulses. Such counters are synchronous and asynchronous. The synchronous counter has all flip-flops connected to the common clock so that all flip-flops are triggered simultaneously. Asynchronous counters are also called ripple counters. The output of the flip-flop on the front is used as the clock of the flip-flop on the back. Asynchronous counter have the advantage that the circuit is simpler than the synchronous counter, but it has also disadvantage, that is propagation delay increases. The asynchronous counter said that is that clock pulses are not only input to the clock pulse input of the first flip-flop, and that the other flip-flops uses the output of each flip-flop as the clock pulse input of the next flip-flop. Asynchronous counters are usually designed as JK flip-flops or T flip-flops, and they have an up counter and a down counter. And this picture shows that the example of the asynchronous up counter and 4-bit. The up counter has a trigger on the falling edge. That is, it changes at the falling edge. Whenever you see the status changes, you can see that the number is up. Since it is 4-bit, 16 numbers changes from 0 to 15 in total. QA has a frequency of 1 divided by 2 of the input clock frequency, and QB of 1 divided by 4, and QC of 1 divided by 8, and QD of 1 divided by 16. It looks like a counter, but it is a clock. Has a different fault. The clock doesn't have a gate. As you can see the picture, there's a difference only in this red circle. You can see in the timing diagram that the counter is on the rising edge and the number is decreasing. And this is the synchronous counter example 2-bit. As you can see this picture, there are 4 states and they're gonna rotate like this. And this is the excitation table, and by using a table like this you can get a formula like this: JB equals QA and KB equals QA and JA equals 1 and KA equals 1. And by using this formula, you can sketch two flip-flops and the connection like this. J and KA equals 1 and JB and KB equals QA, like. And because it's a synchronous counter example, so the clock pulse is going each flip-flops, and the timing diagrams and looking like this. It looks like this.
Hi, this time I'll introduce about multiplier. The most basic form of a multiplier is the product of two binary numbers. This multiplication process consists of calculating the partial product and summing the shifted partial product. A multiplier is generally divided into a serial multiplier, a serial parallel multiplier, and a parallel multiplier, depending on the format in which the data word is handled. The calculation of the partial product is made by logically involving the multiplicand and the associated multiplier bit. This is a set of parallel multipliers, executed and per bit inside the cell, and pass the sum from the lower right to the next cell. The output carry is passed at the bottom of the cell. Let us consider two unsigned 4-bit numbers multiplication in which the multiplicand A is equal to A3A2A1A0 and the multiplier B is equal to B3B2 B1 B0. The partial products are produced depending on each multiplier bit multiplied by the multiplicand. Each partial product consists of 4 product terms, and these are shifted to the left relative to the previous partial product. All these partial products are added to produce the 8-bit product. The logic circuit for the 4x4 binary multiplication can be implemented by using 3 binary operators along with AND gates. In the above operation, the first partial product is obtained by multiplying B0 with A3, A2, A1, A0. The second partial product is formed by multiplying B1 with A3, A2, A1, A0. Likewise for third and fourth partial products. So these partial products can be implemented with AND gates. These partial products are then added by using 4-bit parallel adder. The three most significant bits of first partial product with carry are added with second partial term in the first full adder. Then the results are added to the next partial product with carry out, and it goes on till the final partial product. Finally, it produces a bit sum which indicates the multiplication value of the two binary numbers.